So today I'm going to be talking about collaborative filtering, or uncollaborative filtering, as the little pun says. Just in case you guys are a little bit tired, I'll go ahead and tell you the full talk before I actually start. And so basically, I'm just going to start off with a brief introduction about recommender systems, how they're used, how they're built. Then I'll talk about our use case in particular, so using AWS and Spark for what I'll call medium-sized data at scale. And building a recommender system explicitly for purchase data. So we don't have ratings that we're trying to predict. We're just trying to predict whether or not people will buy something and make appropriate recommendations based on that. I'll talk about how to choose a model and run it on Spark. And in particular, I'll go into detail about item-based nearest neighbor models and matrix factorization models. And then I'll talk a lot, actually, about how to evaluate a model, and particularly a model without any explicit negative feedback. And so a model where you don't have ratings. And then I'll touch briefly on just the importance of presentation in recommender systems. So most, if not all, of the people in this room are probably familiar with the Netflix Prize. So Netflix offered $1 million to the team that can improve their recommender system by 10%. So a 10% increase in root mean square error. And this generated a lot of research on recommender systems and basically improve the field. But not every recommender system is the same, right? So when Netflix was doing this, they were primarily a mail-based system. They had a long latency between when they would send something to person, when they would rate it, and this really affected the way their recommendations were used. Now they're primarily sort of online, and you can see there's a lot of online recommender systems just everywhere. And so when you're building a recommender system, the things to keep in mind are really sort of what do you know about the users and the items, whether or not there are ratings, and how is that rating system used by each user. So even if you have ratings, you need to scale it for users. But if you don't and you're trying to recommend based on purchases or views, what does it mean if someone didn't purchase an item, right? Does that mean they hate it, or did they just didn't see it? And also, does looking at an article mean that it's a good recommendation if someone flips to something and then flips right off? Probably not, right? And so even how you generate your positive data for training takes some thought. So there's a lot of ways that you can start out building a recommender system, and this is just sort of a stolen slide off Wikimedia Commons showing the broad categories of recommender systems. So there's collaborative filtering models, which are sort of taking the wisdom of the crowd to try and make recommendations based on what other users did. Those can be broken down into sort of broadly neighborhood-based approaches. So similar items or similar users are used to make recommendations. There are model-based approaches, so things like matrix factorization. Basically, you're trying to come up with some description of the features that are important. And then, of course, you can combine those types of models. There are also content-based models. So if you know things about the users, if you know things about the items, you can take that information and try and combine it to really make a good recommendation for this particular user will like this particular item based on what we know about them. And of course, you can combine those types of models again to make recommendations. So when you're building a recommender system, you really do have to take into account not only the type of data, but also sort of the scale of your data. So not all recommender systems really scale, particularly to very large data, but also you need enough data to fit your model. So if you're going to run something like matrix factorization, in the classical forms, this actually was really difficult to do. There have been some developments of more scalable algorithms for matrix factorization, which make this possible. But again, you need to take into account sort of how many users, how many items you have, and deal with that appropriately in choosing your algorithm. So our particular use case at Salesforce was basically that Salesforce is sort of a repository for other companies' data. And so this data comes in, it's very siloed, it doesn't touch other companies' data, both for legal reasons and in our case, actually practical reasons. It's much easier to deal with as a siloed bit of data that may be, medium-sized. Some of them are large, but most of them aren't that big. And so it's much more practical to sort of fit a model based on one company's data to make recommendations. But we have a lot of companies, and for each company, we want to fit a model, make some TopK recommendations, and this actually rapidly adds up to sort of a big data problem, right? So it has to be able to scale. But I mean, it's nice for us, right? We don't have to deal with this behemoth data set. So what would you do if you did have to? And there's sort of a couple of options that you can take for dealing with really big data. One is, of course, just to make your algorithm better. And if you don't want to do this, fortunately, there are a bunch of people who have already sort of worked on improving these algorithms. There's a ton of papers out there, and so you can implement what they've done already. Another good option is actually just to make your algorithm simpler. And so you've all probably heard the adage that more data and better data is better than better algorithms. So if you're smart about your features, you can get away with a much simpler algorithm. And another thing you can do is actually try and break your data down. So we fortunately had companies that we could focus on, but you can do things like try and break your data into business groups. You can try and break it into a focus on items instead of users, or even types of items if you have metadata about the items. But one of the important things is to actually just build for scale. So make sure that your infrastructure is going to be able to deal with the size of your data in whatever form the model is going to take. And so the infrastructure that we chose was actually to go with AWS and Spark. And so this is nice for us because we needed something that would rapidly scale, going from a couple of pilot users to basically as many people who wanted to sign up for the new terms of service and get this particular product. And AWS is really great for that. And we didn't want to reinvent the wheel. So Spark has great machine learning libraries. You don't want to go re-implement a commodity algorithm that's been implemented 1,000 times. And so we could really use that to build on top of. So what we actually wanted to build was a TopK recommendation list, right? And so these companies have very different data within them. And some of them have things like product catalogs. Some of them have metadata that we could have used. But the only thing that we were really consistently sure was in every company was purchase data. And so that was the place to start to really build something that would generalize across all these companies. And once we've got that, we can bring in other pieces of data to sort of improve the model. So given that kind of data, the question became, well, what models do we want to start with? And if you look at the data, so I have here just sort of an example of what it might look like with just purchase data. You have something like a user ID, a product ID, and maybe a date of purchase. And this is called, unary, binary, implicit data. But all of these, whatever you call it, it basically does require some special consideration in how you model it. And so there's a number of good candidates for these kinds of data. The first is item-based nearest neighbors. And the second is matrix factorization, specifically for implicit data. And so I'll go into the details of what that difference is later on. There might be some other models that you could try. I'm going to argue that these are the best ones. You don't really want to go into a restricted Boltzmann machine at your first pass. And so these are the two models I'm going to talk about here. And I'm just going to emphasize continually throughout the talk that evaluation of the models and getting the evaluation right for the type of data that you're using was really important. So to talk a little bit about what these models look like, basically item-based nearest neighbors is a really nice model, so it's simple to compute and explain. It tends to be more stable and scalable than user-based recommendations. And basically, all you need to do to show it is do something to compute a similarity matrix between items. And so in this case, I used Jacquard similarity. So basically, the intersect of the users who bought item A with an item B divided by the union of the users who bought item A and item B. And then in order to compute a rating based on that, so you get your similarity, you compute the most similar items, and that's your neighborhood. To compute a rating with that, you basically take the similarity for all the items in the neighborhood for a particular item that you want to rate. So a rating for a particular user, a particular item, similarity for all the items in the neighborhood, and basically multiply that by the ratings of the user or whether or not the user purchased a particular item in the set of items the user has purchased, divide that by the total items in the neighborhood, and that will give you your recommendation. So an example of what that looks like is basically if you have a user who has purchased a hat, then you might recommend to them a coat, a scarf, and gloves, but you wouldn't recommend jeans and a table. So I am going to show you just a little bit of Scala code now. And basically this is to say, so item-based nearest neighbors is not implemented in Spark, but it's a really simple algorithm to compute. And so I have 2 slides. They don't have that much code, and I'm just going to walk through it quickly. Basically, so this is computing the Jacquard on the top, and you're passing in the sets of users who purchased item 1, or product 1 and product 2. And then you just take the intersect, and you take the union of those sets, and then divide them. And so that's all very nice and simple. In order to compute the similarity map, what you do is basically, I'm assuming that you're passing in an RDD of ratings, and ratings are actually a case class that's just part of the Spark recommendations package. And so you go ahead and group by the product, and then get the sets of all the users who bought those products. You take the Cartesian of the products and the user set with itself. This can be really expensive, and there are ways that you can sort of limit this to only products that have at least one user in common. But let's just say, for simplicity, that you take the Cartesian. You filter out products that are the same as themselves. You don't care about them. Then you go ahead and compute the Jacquard similarity for all of those users. And then given those similarity maps, again, you group on product, take those similarities, and take the top most similar products to get your similarity map. And so that's all you need to do to train. The second slide is just what you need to do to actually produce a recommendation. And again, so you have a particular user that you're trying to predict for, a particular product that you're trying to predict for, an array of all of the products that a user has purchased, an array of all of the similar items for the particular product that you're trying to recommend. And then to compute the recommendation, again, you just sum across the item neighbors map, and that's your divisor. To compute the similarity, basically, you look at the products that the user purchased, go ahead and get the similarities for the items in the map for those particular purchase products, and that's your numerator. Then you just divide the sum of the neighbors for the purchase products by the total sum of the neighbors, and that gives you your rating. And that's pretty much it. That's all you need to do to implement nearest neighbors in Spark. So not too bad. Matrix factorization is sort of the model-based approach. And the way to think about this is basically, if you think of your total space as basically a matrix. So users are the rows, and products or items are the columns, and basically each element within that is whether or not they purchased or what their rating was. What you're trying to do is come up with 2 new matrices, one for users and one for products, that have less dimensions, that still describe everything that's going on in this larger matrix. So it's describing all of those interactions, but with fewer dimensions, so finding an underlying representation for what's going on. Fortunately, implicit matrix factorization is already in Spark, which is very nice. So all you have to do to use it is basically import the appropriate library and say, all right, ALS train implicit, and then pass in your parameters. So very easy to use. And then basically the difference between implicit and explicit matrix factorization is in this equation over here, I guess on your right. And if you don't want to look at that, there's the text from Spark. But basically, what it's doing is in most matrix factorization, if you look at the first, the terms in the first set of parentheses, that's what you're trying to minimize in regular matrix factorization. So you have a user preference, so P for a particular item, and you're trying to minimize the difference between the multiple of the user factorized row and the item column. Basically just minimizes some square error within that. For implicit data, you're basically adding on this second term, which is C, or the confidence in that purchase. So it's basically separating out whether or not something happened with actually how confident you are that that means the person liked it. So it's putting in this additional term, this wiggle room, that really allows the model to fit implicit data much better. And that confidence is 1 plus alpha, which is a hyperparameter that you tune, times the rating, or the number of times that the person purchased the data, and then the preference just becomes 0 or 1 based on whether or not they purchased the data. And the second part of this term is just the regularization. So with matrix factorization, there's a lot of empty spaces within that matrix that you're trying to fill in. You want to make sure you're not overfitting to the data, and so you put a penalty on the terms that you fill in with your matrices. So great, so those are our two models. How are we actually going to select between them? And there's a lot of metrics to choose from. So with implicit data, you probably want to pick something from this screen. But basically, some good options might be precision and recall. So you have things like the number of true positives that you predict versus the total number of positives that you predict, and that's your precision. Or you could have the recall, which is the number of true positives you predict over the total number that you could have predicted that would actually be positive. You can do the F1 metric, which is the harmonic mean of precision and recall. And then there's the classic sort of root mean square error, which is used for a lot of things. Area under ROC is, again, related to true positive and false positives, in basically looking at how different from chance is your model. And then there's also some ranking metrics. So if you're presenting a list, you can do things like see where in a list your items occur. With mean reciprocal rank, you can use discounted cumulative gain if you have a true ranking to basically say, okay, so given the rankings that I gave, how close is that to my true ranking? And basically you have a metric of the difference between those two. But none of those metrics actually solve a fundamental problem with implicit data. And that's basically that there's no negatives, right? So if you look at this data and sort of work through the classic machine learning process, if you have your original data, and again, that's like the user ID, the item ID, the data purchase, and you divide that up into your training and validation, and then your test sets, and this can be separate training and validation or cross-validation on your training, it doesn't matter. The problem still remains that you basically only have ones if you think about the ratings, right? And so the best fit to this would actually be a model that predicted the user would buy everything, which is not at all useful. And so you have to get around this. You have to have some negative data somehow. And there's a couple of ways that you can do this. The first is actually to just generate some negative data. And so you can basically say, okay, some unassigned values that the person didn't buy, I'm going to say those are negative. And the reason this works is that if you think about the total space of users and products, it's very large. And the actual relative space of products the user will actually like is much smaller. So just randomly assigning things from that very large space as negative will probably be correct. And so this actually does work. It's a bit of a hack, but it'll give you something you can work with. Another option is actually to generate a list and focus on the TopK recommendations. So does your holdout set actually appear in the list that you're recommending? So there's just a couple things to consider when you're deciding between, this sort of matrix of how am I generating negative data, what are my metrics that I'm going to use, and it's this kind of thing of actually considering what you're trying to do. So are your results going to be a short list or a long list? This actually makes a big difference in what kind of metric you choose. Are you predicting a rating, or are you trying to predict whether or not someone will purchase something? So is it actually just a hit or a miss of whether or not they'll purchase? And then the other thing is actually just to be aware of the biases in offline training. So if you're doing a TopK recommendation, this will sort of skew towards popular items, which can lead towards less personalization. And then things like ROC, precision and recall, will actually not tell you anything about how good the ordering is. And so if you need that information, this might not be the right metric. And finally, it's just really important to remember that offline evaluation is not perfect. And so you want to go ahead and test in the wild. That's what this guy is doing. He's testing in the wild. And so remember that models have a lot of different levers that you have to tweak. And so just an example of what that looks like, this is one set of relatively modest grid search for hyperparameter tuning for implicit matrix factorization. As you can see, so the rank of the matrix that you're trying to fit, your regularization parameters, how many iterations until convergence, and then your confidence value for the fit. You can see this rapidly adds up. You could be running the model 250 times. This takes a lot of time. And it's time and resource intensive, but you really can't get around it because it has a huge effect on model performance, and it's really data set specific. So you need to do it for every data set. But fortunately, if you have flexible resources and Spark, you can parallelize this and actually make it happen much faster, as long as you have the right evaluation metric. So what is the right evaluation metric? So I'm just going to start off by saying it's not root mean square error. Not with implicit data. So what I've plotted here is basically the root mean square error on a number of runs for different models with different hyperparameters against the number of true positives actually predicted by the model. So how often is the model correctly predicting that something would appear? And this is for a case where I just generated false negative data. So one thing to keep in mind is, of course, that this depends on the number of false negatives that you generate. But more importantly is actually that this just isn't very helpful for predicting. It's not even correlated with the number of true positives that the model is predicting. And it's not really showing good differences between the models. So if you look at alternating least squares explicit, so matrix factorization for explicit data, which is inappropriate for this kind of data, you can see that it actually covers the same range about of root mean square errors as alternating least squares implicit, so matrix factorization specifically for this kind of data. It's not showing you the differences very well between those two models. However, if you look at the true positives, it's clear that the appropriate model is doing much better, right? So just don't use this metric if you're trying to evaluate. Something that will work is, for example, hits and misses. So again, this is with generating zeros for the data. And what I've plotted here is the recall on the y-axis versus the precision on the x-axis. Again, I'm showing 3 different types of models with different hyperparameters. So basically, you have the alternating least squares explicit, the inappropriate model. You have the alternating least squares implicit, so the more appropriate model, and you have item-based nearest neighbors. What you can see is there's actually a nice trade-off. So there's a trade-off between precision and recall, which you expect, and then it's showing differences between the models. So the implicit matrix factorization is actually doing better on recall, but slightly worse on precision. And so if you're using the F1, you might choose item-based nearest neighbors for this particular data set. So one thing to keep in mind is that this will, again, depend on how much negative data you generate. But as long as you keep it consistent across models, you can sort of compare between them and really get a good idea of what's going on. If instead of generating zeros, you want to look at the TopK results, basically you can say, given my holdout, what percentage of those actually appear in my list that I'm generating? And if you're presenting a short list, this is probably a good way to go. And what I've plotted here is just item-based nearest neighbors versus alternating least squares implicit, so the appropriate matrix factorization model. And what you can see is they're somewhat comparable in this particular case, but there's a big difference in performance or recall based on how many items are in your list. And so basically, if you're presenting a list of something like 50 different items, this may not be a good metric because chances are users aren't going to look at the 50th item. So giving the same amount of points for something at the end as at the beginning isn't really going to help you. A couple more things to keep in mind with this is, so you don't want to look at precision in this because it's entirely dependent on the length of the list. And if you're presenting a really long list, again, you have no way of knowing how good the other k minus whatever your holdout set is. And those are the really interesting things, right? Those are basically the novel recommendations. And so that's where it becomes important, again, to follow up in the wild and make sure that you see how users are responding to those and really get evaluation after you present it. But going back to what to do if you're generating a really long list, users may or may not look all the way down. You may want to move to something like a rank metric. So I'm going to argue that discounted cumulative gain is going to be a little bit tricky to do here, and that's basically because it's hard to get truth data for rankings, for personalized recommendations for a large data set, right? And so using something like mean reciprocal rank will actually give you something where if your item is appearing at the end of a list of 50 items, it'll be penalized much more than if it's appearing, fifth in that. And you basically want to make sure that you're appearing as high up as possible in that really long list. And so the way this works is, say you have a list of 3 results, and the one you're looking for is cats. Then basically you would give that list, if it appears third, it has a rank of 3. The reciprocal rank is 1/3, and then you average that across all the queries or all the lists that you generate. So this will really give you a good metric for long lists. So which do you want to use? Basically TopK or generating negatives. And again, this depends on what you're trying to do, right? Fortunately, the results are related. So you can see that there actually is a nice correlation. So what I've plotted here is the recall for generated zeros versus the recall for a TopK list for the 2 models, different hyperparameter runs, item-based nearest neighbors versus alternating least squares, implicit data. And basically, you can see that you'd be able to somewhat use the results from either one, but you'll probably get better results when you actually go and implement your model if you just make it as close to what you're actually going to present as possible. And so if you're showing a list, you probably want to use TopK. If you're trying to predict whether or not a user will purchase something, you may want to do just generating negatives. It is important to keep in mind that actually TopK can be a lot more computationally expensive to generate. So, use at your own risk of spending a lot of time staring at jobs, not running or not finished running. All right, but anyways, what's the best model, right? I spent a long time talking about how you evaluate models. What's the winner? And it depends on your data. So again, it's sort of a theme here. But basically, I've run the models on 3 different data sets here. So these models, or the data sets basically have, so I think one of the data sets, data set 2, I can't remember. One of the data sets is much bigger than the other 2, and one of the data sets is basically much sparser, so it has a lot more items that are infrequently purchased. And what you can see is that it actually makes a big difference in which item wins. So this is the best tuned model for hyperparameter tuning for item-based nearest neighbors. You can see that it does the best on the first data set. Whereas the alternating least squares matrix factorization does the best for data sets 2 and 3. Unfortunately, the inappropriate model, the explicit matrix factorization, does the worst on all 3 data sets. So that's at least something. You can narrow it down to appropriate models if you're really hoping to do well. But this really just goes to emphasize that exploration of the models combined with good evaluation is very important. But the good news is that you can actually get decent answers across a wide range of data, and so you don't have to be very, very specialized in how you're doing it if you've got your evaluation correct. One other consideration, and so I mentioned this briefly, is just sort of the processing time for models. And there's not much you can do about this except try and sort of work around it and keep in mind how often you can get away with not refitting your model. And so again, this will kind of depend on how your data is structured more than size. So in this case, dataset B actually was an order of magnitude bigger than datasets A or C. But what you can see is that dataset C actually took a lot longer to run for matrix factorization, and that was just because it had a lot more items and users. So the size of the matrix was actually the determining factor rather than the number of purchases. And so there's a number of things that you can do to sort of decrease the impact of fitting time. Basically, for both of these models, you can sort of pseudo-update, so use purchases that happened since the last time you ran your model, and basically try and artificially freshen your results that way. And this can decrease the need for refitting your model, make it go stale less quickly. And the other thing to consider is actually serving time for your application. So if you need results to appear very quickly and your model is taking a long time even just to compute a recommendation, you may want to consider doing something like batch jobs. But again, this has the trade-off of making your data a little bit staler, right? So if you're computing batch jobs once a day, you're not going to be able to take into account what they just purchased. So beyond the purchase data, which is, of course, what I've just spent this whole time talking about, you may want to incorporate other kinds of information in your model. So if you have metadata, and we do want to incorporate this, basically the purchase data is a starting point. For companies that have additional data, we want to make our models better, bring it in. And so there's things like product catalogs that we want to use, so information about the items, information about the users. I mean, you can do a lot with even just IP address and a geo lookup. Item popularity can actually be a huge thing to incorporate into the model. And so I'm not going to talk about it, but I'm just going to basically say that the way you incorporate this information is through a process called learning to rank. So you have your first recommendation score, and then you would have something like item popularity. And basically those provide 2 scores. You come up with weights for each of those scores and combine them to produce a new score through learning to rank. So the final point that I'm going to make is actually just around presentation. So the cold start problem is a big deal in terms of what you're going to show people. So what happens when you get a new user? What happens when you get a new item? So with new users, it can actually just gain you a lot to show the most popular items. So we saw better than a 20% lift just by showing the most popular item for new users. But for new items, you actually treat this differently, right? You don't want to get into this sort of loop where you have a new item, so it's not in the recommendations, so people don't buy it, so it's not in the recommendations. New items, sort of lifting those up can be really important. So you may actually want to have sort of a special space for new items. If you have metadata about the items, you can use that to sort of boost them into recommendations. But basically, the point is that you really have to take into account business logic, make sure that the ultimate goal is coming into play with your recommendations. So recommendations are a tool. You want to make sure that it doesn't run rampant, right? So you have checks on it. You make sure that it's really doing what you want and serving all the use cases. And beyond the right model, it's actually really important how you present these recommendations to users. So just the phrasing, so telling people you should really buy this versus people also bought will have an effect on what they think about it. Whether or not you include a picture is actually a huge difference in whether or not people will actually click on your recommendations, interact with them. And so when you're testing the model, you also want to test the presentation and just make sure that the presentation is doing the best job that it can to make your model effective. And it's not just the actual box that your recommendations appear in. It's actually the context of the site, right? So basically, when users are coming to your site, what do they expect? Are they looking for their friends on Facebook? Are they going to be really insulted if you recommend someone that they hate? Are they looking for a book recommendation? What is their response going to be if you recommend them 50 Shades of Grey? Like, is that going to be upsetting or not? So keeping that in mind, you may have to have additional rules in place just because of the context of what you're doing. Right. So in case anyone zoned out, basically I'll just summarize what I was saying. And basically, the important thing is the tools are out there, so don't reinvent the wheel. Like if you can use someone else's library, use it. You can always add more to it, but it's silly to spend time rewriting things that have been written a million times. Machine learning algorithms are big and iterative, and Spark is actually really good at these kind of processes, much nicer than trying to do them in Hadoop, in my experience. And the real key here is that you want to think about your use case. So you want to let your data dictate your model, not use your favorite model no matter what. Think about what you're trying to do. Think about what your data looks like, and take that into account. When you choose your model, consider your evaluation in terms of your goals. So get as close to what you're actually trying to do as possible in your offline evaluation, and then continue to test in the wild. So continue to test after you put it into production, see how it's performing, reevaluate your model, and continue to improve it once it goes live. And then finally, the details of presentation are important. So the best algorithm in the world is not going to overcome a terrible UI. If the user doesn't see it, if they don't like what they see, it doesn't matter how good the underlying recommendations are. All right, thank you.
Great. So do we have any quick questions? We're kind of running a little late, but...
Can you talk about the uncollaborative feature of your approach? More specifically, how did you define your neighborhood?
Sorry, in the nearest neighbors, or just the pun in the title?
Yeah, the pun in the title.
Oh, the pun in the title. It was basically just uncollaborative in that the users aren't helping you out by giving you a rating. Basically, you're having to infer based on their actions on the website. So based on whether or not they purchased something, based on whether or not they viewed something, without anything explicit from the user.
That's on the top of it. So they are kind of helping.
So not intentionally, right? They're not intentionally helping you. You're just taking what they do rather than. So by collaborative filtering is generally applied to this whole rating. So you go, you watch a movie, you tell explicitly Netflix how much you liked that movie, which is very different from the current model, actually even at Netflix, where they're basically saying, so we want to know if a person liked a TV show. If we recommend it to them and they watch it once, like one episode in that series, does that mean it was a good recommendation? Probably not, right? If they watch a significant portion of the series, then it's actually good. And so you're having to infer that rather than the user telling you, is what I mean by the uncollaborative part.
Awesome. Maybe any more quick questions? All right, here's one.
The Jacquard algorithm that you showed, have you thought about pushing that back inside of Spark?
So I had looked, and there was a ticket in for a nearest neighbors algorithm. It wasn't specifically for collaborative filtering, item-based nearest neighbors, but basically I decided that since there was already basically a bunch of people working on a nearest neighbors algorithm, it wasn't worth it to push it back in.
So then do you know if that'll be in 1.5 or?
I haven't kept up on the ticket, so I just saw it was there.
Awesome. Well, I think that's leaving us with no time, but thank you so much, Leah.